this. So news for today, course surveys are on and we have 0 responses. So in order to get a few responses, we'd like to remind you of what is this about. We'll give you some time on Tuesday to fill out course surveys. What they're good for, I don't know. And this is please share your feedback. This is the first offering of this course. So the course resembles, maybe 2/3 resemble 241B, but 1/3 is different and it's new and things are in flux. Feel free to tell us how you feel about that. Would you like an incentive? If everybody responds, you get some percentage of a grade. Would that work? I mean, it doesn't change anything, but maybe you'll feel better. Yes, no? You don't want, in exchange for 85% turnout, a 0.5% of credit? All right, I mean, what we're offering, we'll see, we'll remind you next week what's the incentive here. That works with undergrads reasonably well. Okay, so what we, yeah.
So is the final exam actually next week or is it during the finals?
No, it is the next week. On Thursday is the final exam. As announced in the first lecture. It's an 18-minute exam. I'll mention it here. The format is 80 minutes. It's like 4 quizzes in sequence. The reason why we do it in the last class is because a lot of people take 240B together with this class, or sometimes 252. And I think there was, when I was teaching this, there were massive complaints when they would schedule 241B and 240B one after another. I mean, they love to do that, as exams, right, one after another. How would you feel taking 240 and 241B in sequence? There is no? Oh.
We have the final presentation at the exact same time that we have the final presentation.
240B doesn't have an exam anymore. It used to have, oh well, and there is no exam. There is no that collision, but the decision has been made. So I was fielding massive complaints, that this is not, humane. This is unnecessary stress to have 2 exams on the same day. And then, also 252, the other people who had 252 also would have an exam on the same day. So 252 got rid of the final and has just the projects. But we need final because people don't retain this stuff unless you read it at least one more time. Again, there is no retention. That's what we found out. And doing that for a prelims class is not a good idea. You anyways have to study. So if you do it 3 times, there is a much better chance that you're going to remember.
And the final project is when the presentation happens.
Yes, I mean we have some slip time if you want a day or so, but we would like to wrap this up.
When are our presentations?
Thursday morning during the reading week. A little more work. So each question is, if there are 4 questions, they'll be about 15 minutes long. If there are 3 questions, maybe 20 minutes long. There will be an analytical part and maybe a multiple choice part. But they'll go topical, organized around the areas that we have covered in class. Okay, so what we have covered last time, what we covered were the basics of the operation of phase 1 loops. There are a few things that are important there. They're generally used for clock synthesis on modern SoCs, and a modern SoC has a number of phase lock loops now, a number of clock generators that are in there. There are some interesting properties that you have covered over there that I wanted to you to remember. It has a low pass function. PLL generally has a transfer function that is a low pass with respect to reference clock input, and it's a high pass with respect to VCO noise, right? So anything that couples at a high frequency to VCO will show up at the output. We're going to see importance of that a little bit later. But I'm going to cover another important part of a clock generation very briefly now, significantly easier, which are the delay lock loops. Delay lock loops in here are shown to in comparison with a PLL and what we have seen before. PLL generally has a few components: a phase detector, a charge pump with a filter, and a VCO that is being controlled by the signal that is being filtered out of the charge. In most digital systems nowadays, this is a digitally controlled oscillator, and it is controlled by a digital number over here that comes out of a digital filter. What kind of filter is this? This is an RC filter of low pass. In control theory, what are the properties of that filter? Proportional, integral, or differential? It is integral, although by arranging the filter, you can have some proportional, you can have some direct feedback in there. PLL controllers now are more complex. They may be proportional, integral, and differential. Just a quick recap. What does integral control do? Basically inserts memory into the system and accumulates any kind of a phase error that is in there to try to cancel the long-term averaging effects. What does the proportional do? Only instantaneously, if there is any change in the phase, in the input, it tries to get the PLL to respond to that again, but that is going to be blended with the integral form. What is differential control? It's anticipatory. If I see the signal changing in a particular direction, I'm going to try to change the frequency, anticipate the change. We'll see that that is something that is important that exists in PLLs nowadays, trying to anticipate what is going to happen, for example, to the supply voltage and change the frequency in response. PLL put the same, there are delay lock loops, and they, instead of a VCO, they simply a delay lock. And what they want to do is to lock the phase of your signal again to the input signal, but only by changing a delay, not by not changing the frequency. As a result, that loop is a lot simpler to control because it is inherently a first order loop, meaning it has a single pole unless we have any other kinds of parasites. What is good about the single pole things, first order systems?
Always stable.
Perfect, they're all inherently stable. That means you can't mess it up. You usually will not make it oscillate when it's not supposed to. I mean, unless you add some of the additional parasitic poles. There is no filtering of the input, which is the reference clock whatever the input will come out to the output. And it is generally constant frequency, meaning that it is not, unless we add another, some additional components, that it is not used for frequency synthesis. Although you will see these hybrid approaches where there may be another component that has a second order loop to it that can be used for frequency synthesis and doesn't accumulate phase error. A simple example over here, it is going to try to shift the output signal to be aligned with the input signal by, running this up-down charge pump pulses so that until the delay signal is aligned with the input signal, and then when the error signal is zero, it stops adding any pulses to the charge pump, but neither up nor down. If you go ahead and analyze it the same way, analyze the regular fuel, basically cut the inputs in here and try to find out what is the open loop response and then find what is the closed loop response, where you're taking delay as the variable in here. Very simply, you'll find out that the out open loop response is V out over the difference of VI minus V out with the loop open with single feedback single tap over here. It'll be KPV times 1 over SC, if this is an ideal just integrator, single capacitor, times some proportionality ICP times KVL times FF. If you find a closed loop transfer function for these two, it is a single pole. So the transfer function of the delay is low pass filter. Okay. So that's it. It's basically being used for aligning clock signals such that there is no phase error between them. We generally need, because it does not provide good filtering of the input, it require low jitter input. But it adds new additional noise sources, as Vladimir has mentioned. There would be delay line that is sensitive to supplies, clock buffers, and perhaps a small impact of the device noise. We'll see applications of DLLs in a second. So finals in class in a week, it's 80 minutes. So it's not too scary, about 4 quizzes in a row. We eliminated the 4th quiz because we realized that it would not be productive to run yet another quiz. And then we have project presentations on the 5th of May in BWRC. Remember, we are going to try to keep you strict to rehearse 12 minutes plus 3 minutes for Q&A. Yes, the project reports are due at the same time. We can give you an extra day if you need to turn them in. We'll talk about project reports next Tuesday. But generally, they're 6 pages, journal kind of articles. Okay, the next topic, clock distribution. In general, clock trees, the goal of a clock tree is to distribute the clock signal across the SoC with as low of a skew as possible. Perhaps better said is to do it with as low a skew as practical. Achieving zero skew is not practical because it will generally burn too much power, something that is a corollary of what we have talked about when we talked about optimizing delays. Clock load is enormous in modern chips. It has not been really published recently, but what you're going to see is something of the order of hundreds of nanofarads. So in order to drive something like that, so you have a PLO on one side and then this enormous load on the other side. What do you need in order to do that?
What is it?
In order to do that, you need to build a buffer chain. It's not really built as a simple chain, it is built as a tree. And what you see here are different types of trees that people use. So it also distributes things across a very large area. So your resistance of fault lines matters. And as you do that, it is common that people will be using some kind of a paper line where the wires are going to be wide. So often you will find out there is classical topologies of trees and H trees. Essentially, you're driving a channel that's one inverter in every stage of a clock tree. But a better skew is achieved by shorting the outputs of these buffers at certain levels, maybe at the final level or some of the intermediate levels of the tree. The result of that is lower skew, but higher power, because you do have to deal with fallout that's there are also grids and meshes that people have built out of that, where they basically short out everything, drive something with very large buffers, and then short all the clock distribution at the very end. In practice, it is not practical to have anymore a clock tree, uniform clock tree across the entire lifestyle. There is a credible campus-wide threat. Here we'll find out what it is. And if you feel freaked out, fine. Luckily, we're very close to. Usually, we're okay inside of the buildings. We haven't had this in a while. This happens in the finals week, by the way. Those of you who are new to Berkeley. We haven't had it in a while. So, in general, it is not practical to keep the entire die synchronous. Most approaches nowadays have these synchronous islands that correspond to a core or a tile inside of a chip that is being kept synchronous because of impracticality of keeping everything in sync. And here is examples of clock systems, how they look like, where there was a global clock grid that was over there that was being driven from different sides, and often they would feed back that output to the PLL to control the skew between different phases of the system. There are a few other interesting illustrations of how these things work. So this is showing from around the same generation power port about 20 years ago. This is showing X and Y dimensions of the chip on the bottom are X and Y dimensions of the chip. And here's the delay of the chip. The first really important thing to note here is that from the root of the tree, from the leaves of the tree, the delay is about a nanosecond. that is more than the clock cycle. Even back then, it was more than the clock cycle on this processor. So any change in frequency that may happen at the input of the tree may take a couple of cycles to propagate to the end of the tree. With branches, that growth that became bigger, it was typically, something over of the order of 2 to 3 cycles. However, when you look at many of these systems that are now only locally synchronous, that is still being kept at a couple of clock cycles. There is something really important about this. Because of the delay through the clock tree insertion delay, you cannot change things in a single cycle. It's impractical. You have to be able to anticipate things if they're going to happen quickly. Relate that to the differential response of the PLR. Okay, and this is showing some other interesting things. The fatness of the wires is showing how much current is going through them. So those are big and fat. As it became impractical to drive the entire tree with a mesh, the multi-core systems started designing multiple clock trees. And this became particularly interesting when we have started seeing variable frequency. This is an example of Intel HD clock star that was implemented in the K2, where there was a single PLL, and it was if you remember, titanium. That was a long time ago. That might have been still in elementary school, or maybe kindergarten, or something like that, preschool. There were 2 cores that were operating independently of each other. Each one of them had, was able to vary frequency independently of the other one. So what you would find here was, a structure that is representative of what we see nowadays. There are these digital frequency dividers and clock buffers that are building on the tree that went all the way to the gators. Clock gators are a big disturbance in the entire system, and we're going to see those in a second. They essentially built delay lock loop around the whole thing by utilizing these, permeate delay lines, which are very fine delay on the whole thing that work going through the scan chain, mostly static. So this whole thing brings us to the modern day, and I'll go through the roots of how modern day clock distribution is being done in processors, often through the concepts of deskewing and synchronization. The first thing that I do want to mention is nomenclature. Some people are very confused about how things are, what does this mean? But simply based on how different parts of a system operate at which frequency and which phase, they're given their proper names. So if the 2 things that are trying to communicate with each other have the same frequency and the same phase, we'll call them synchronous. If they have the same frequency but different phase, we'll call them different phase, but with a constant offset, we're going to call them mesosynchronous. What's synchronous are the ones that are kind of drifting from each other, what we typically see in communication systems. The transmitter is transmitting from one clock source. The receiver has its own clock source. They're not the same. They're slightly different frequency. As a result, we need to recognize that frequency and adjust it. And finally, if they're not related to each other, the two things are asynchronous. If they're synchronous, and there is not, we are going to drive the whole system as analyzed as a synchronous system. If the system is mesopronous, what does that, what do we do to eliminate the constant phase offset? DLL to rescue things. In plaseuchronous systems, we generally need clock and data recovery loop to receive a signal from, say, a DRAM or some other device. In asynchronous signals, we need to resynchronize. We'll see some of that as we go along. I will not talk about clock and data recovery loops. That is a lot. That's a half of a separate topic, separate course that we have. I'll spend a few minutes talking about DISQ systems, which is basically a mesopronous operated system. The roots are 25 years old, and this is what was done even back, 98, to try to ease the burden on driving a big clock grid from left and right hand sides. So this was a big clock mesh, a grid, whatever you like to call it. It was over a clock core, over a port or microprocessor. It was driven to two sides with a few millimeter wide buffers. I mean, this is literally a very big inverter where W is in millimeters or maybe in centimeters. There is some combinational logic that is being triggered from the left-hand side and the right-hand side of the spine, and they meet somewhere in the grid. The idea here is you can measure the difference between those clock phases that are relatively small, and attempt to, there is a discrete Q control, and there is a delay line on the left-hand side and the right-hand side that is going to act through the control loop to minimize, to zero out this difference. The difference may exist because of process variations or temperature or something like that. So you can view this as like a global, very large delay loop. You'll see that multiple times over, in production, and this is something that we also often see nowadays. There is a PLL in here that drives the main clock. There are skewers that are operating in different parts of the system for regional distribution, and then local distribution is derived from that. However, when you arrive, the leaf nodes, if any of them needs to talk to another leaf node, if there is no loop here, we will have to resynchronize. And that is a typical thing how things are being done today. Typical approach how things are being done today. So here is how does the DISQ, how did it used to look like? Essentially a DLL to align regional clock with the reference clock for each of the regions on the chip. The more recent ones, you can look at typical ICC papers now, and they put even less information now than they used to. But what you'll find out are many of the clock domains here are driven by now separate PLLs. And that is totally reasonable thing for, say, peripheral circuits. So what you'll find out here in the Xeon about 7 years ago, we had a range of signals that were used for clock DVR for different PCI Express lanes and so on. PCI Express QPI, that's another impulse interface, and force. One thing that you will notice is, interestingly, they were using LCPLLs for signals like PCI Express and QPI, more higher frequency signals. And these self-biased PLLs were used for signals that can tolerate more logic. So self-biased PLLs were essentially, the VCO was a DCO that was digitally controlled and had some self-bias to eliminate, to decrease the supply noise. But high frequency interfaces were operating on things that look like an RF PLL, LC type PLLs, where the oscillator was an LC to achieve lower power for the desired phase noise. Now, what happens here when we try to put together a complete system? So there is a main PLL that drives a whole bunch of the others and provides a reference for the others, and then it supplies all the clock domains. When we need to cross the clock domain, here is a situation that we will encounter. One clock signal, one clock domain will be the source, and there will be a receiver in the other clock. The phase relationship between the two signals is unknown. We probably know the frequency relationship, but we don't know the phase relationship. There is some delay that they talk through, maybe zero delay, or there may be some buffer. And now what happens here if this flip-flop is supposed to receive that signal? Most cases, it'll be fine. If there is no setup or hold time violation, it will just receive the signal. Now, what will happen if we are unfortunate and we hit the metastability of this flip-flop? The question here is, you may be propagating the glitch. Not likely. So here is basically what happens when you have a flip-flop. I have remember my picture of a flip-flop, and clock and data have arrived in a way that where data transition is much earlier than the clock transition. I have that. What happens if the clock transition is very close to the data transition? So this is my output Q. And if my clock and data arrive very close to each other, we analyze this earlier. Yeah, the delay increases. It can happen that in some cases in the internal nodes of this flip-flop, it will not really ever, it may just take forever. It may just decide to sit somewhere at the halfway point. And that's like an example of metastability. What do we do when we have something like that? Well, after one clock period delay, we sample that signal again. Probability is that we are going to have signal that is again really, crossing at around VDD over 2 is significantly lower. You can find out, the dissertations have been written about this. It exponentially decreases. So this is a concept of a so-called brute force synchronizer. In general, nowadays, since we operate at fairly high frequencies and there is a many block crossings exist on the chip, probability that the system is not going to receive correct signal is not attenuated, sufficiently by just having 2 plus 1 sample the signal. We generally, what you'll find out in practice, research chips use 2, and that is convenient, but products use 3 or 4 plus 1s for brute force synchronization. What is the trade-off of a brute force synchronizer? What's the price that you pay for a brute force synchronizer? A longer path, you need to wait for a few clock cycles to make sure that your signal is correct. And that's a penalty. That is a penalty that is okay on peripheral interfaces that anyways have long latencies. But it is something that is deadly for like L1 caches, first level caches. So we can't have that. That's why we require to keep things in the same clock phase, clock signal, clock domain. There are other ones that help get around this. Another campus wall. All right.
So this is a synchronizer. So it only works if you're going from like a slower clock to a faster clock. Because if you're going the opposite way, still you might end up with something.
I think it should work both ways. It does not matter on the. It is not. It is just there to adjust for the clock phase. I mean, there may be some. You don't want to lose the data. I mean, you cannot just. I'll show a FIFO type of a synchronizer that is needed when we may have variable rates. But this is brute force synchronizer is in this example is assuming that 2 clocks are the same or very similar, and they just have different phase, unknown phase. For things where you can try to where you would like to avoid paying high penalty, we go through so-called rational. There are so-called rational clock processes. I will not cover those. They're just basically a more streamlined version of this. The question that you've asked about, Ken, is how do we cross between 2 unrelated clock domains that may be running at different rates? How do we exchange information between 2 different rates? So the way how it is done is by using a FIFO, first in, first out, that has a write pointer and a read pointer in it. So write pointer shows where do we write the next value, read pointer points to the value that we read out. And there may be, a few other pointers associated like that, empty, full, or near empty or near full, indicating to the source or the receiver to either slow down writing it or slow down or speed up reading stuff out. The important part of that, I mean, this has been seen actually. Some people in 151 had to design this last fall. Clock crossings here, it's important to notice that the right pointer writes to the other side and becomes the request pointer source for the read side. These two, this is from an FPGA type of design where they use two flip-flops. Modern designs, if it's an ASIC design, it will typically have 3 or 4 flip-flops in sequence for synchronizing the FIFO rate adaptive FIFO. Okay. That's all what I had to say about clock domains and synchronization and T-skewing for now. The next topic is the topic of supply generation. And again, we have entire courses over here about power electronics and voltage regulation. So this will be very quick and brief, just to give you a flavor of what is happening here. You have two types of regulators, linear or switching. And there are two types of switching regulators, capacitive or magnetic. Linear regulators exist of a series or some type. We basically use just a series type of regulator because it's more efficient. But it is still highly inefficient. That's its main disadvantage. If we are regulating, going from a relatively high supply voltage to low voltage, the efficiency is proportional to the ratio of the two voltages. But it is quiet, and therefore friendly to integration. Can be integrated in many chips. On the other end of the spectrum, we have a switching magnetic regulator that has some inductors and capacitances in there and a bunch of switches. Can be made highly efficient. That is what we'll typically find in all the power supplies nowadays. When I, long time ago, used to have, the first computers, would come with a transformer-based regulator, and that would have been a rather complex thing to carry. These ones can be very efficient. So I have something. My wife is now panicking. Why is it a lockdown? So we are apparently in a lockdown now, so that we are not going anywhere. And have a class all day. So I think they probably locked the building entrances.
Well, when I got it,
Oh. Yeah. So this thing is a little harder to integrate. They're a little harder to integrate because they need inductors and they won't be a relatively high value, which is a price for efficiency. We'll see some of the efforts on how it was brought closer to the processor. So, and they're noisy as well. So, and in the thing that is in between them are the switching capacitive regulators that have limited efficiency in between the two. They have poor regulation, but can be integrated. So, a quick note of linear and switching regulators. So linear regulators basically regulate by adjusting the series resistance series. We will adjust the series resistance here to match the varying load that can be varying resistance or current to keep the output supply constant. Switching regulators avoid that. They do some kind of an impedance transformation that always presents low impedance from the load to the source, and therefore are not limited by this voltage division that we have here that is essentially limiting the efficiency. So a linear regulator does not help save that much power or save the energy of the whole system, because whatever we regulate down the voltage to, they're going to spend it still on the regulator itself. The way how they work, and this is our variable resistor over here that is being regulated by a feedback loop. The feedback loop essentially sets the voltage with some kind of an offset to some reference value and drives the output to be something to the reference plus the offset. As the load changes, the feedback responds to adjust the resistances that these values are set at the desired level. These systems do. Did I start recording here? Maybe I did, maybe I didn't. No, it's going recording. So why do people use these regulators, linear regulators? Because they can be integrated on a die, and they can be used to keep the chip running underneath the thermal envelope. Switching regulators, in this case, are shown of a buck type or a step down type, are based on the minimum 2 switches. So these are 2 large transistors that in case 1, this switch is on, the shunt switch, series switch is on, the shunt switch is on. The series switch, when it is on, it will drive the current up to the inductor. When the shunt switch is on, the series switch is on, it will drive the current down. We'll see this ripple of current that will be filtered out through some kind of typically an LC filter at the output to regulate the voltage. The way how the voltage is controlled is by controlling the pulse width. So by changing the pulse width, we can change the amount of the current that is going through and regulate the voltage. The big thing that we have here that bothers digital systems is that we have ripple. So it is not a smooth output curve. It does, voltage current is not smooth. It's not steady. It naturally has a ripple. How do we control ripple? By running these regulators either at a fairly high frequency. However, you can't run them at a crazy frequency, but you can. They typically run them. There was a challenge early on when they were introduced. They were in audible range, so you could hear them. Then they were in the PV range. But now they run, at megahertz or tens of megahertz levels. They generally don't bother too much. The other way how we can try to control the ripple is by interleaving multiples of these and using multiple phases. A very interesting way of how this was done was, some 10 years ago when Intel introduced Haskell as in-package regulation technology. So what they had were these regulators that were almost integrated. They were, they were power transistors, and that were on die, and then they had the inductors on a separate die that was put together in the same package, connected with a whole bunch of units in there. The way how this before got used and how you will see in many systems nowadays, regulators are sitting around the die, and you will see these what are called the DRMs around the processor and many other components. I think the most interesting ones are if you look at these product-based sections nowadays, is what NVIDIA has on their 500 watt GPUs, and the amount of voltage regulators around. So each of these power cells were able to supply up to 25 amps of current, and they had that programmable switching frequency from 30 megahertz to 140 megahertz. They would run 16 phases per power cell, 320 phases per chip to smoothen out the current. That's basically what was in there. One of the big challenges of that thing was that it was more shelter in place. One of the challenges of that, it was a stacked die, so it was relatively thick. That was also the time when people really wanted thinner and thinner PCs, and in particular, in my other laptop, they wanted the processor inside the screen. So it's kind of a problem if you have something like this, a few millimeters thick. They came with another solution in Broadwell that inductors were moved to a small PC that was not stacked on the back of the die. So they did something that was unthinkable at that time. No PC manufacturer would allow you to drill a hole, but because if you're big enough, to drill a hole in the PCB, which you can stick capacitors and inductors in there and reduce the thickness of that hole. So that is what we have essentially nowadays in production. So switching regulators are typically somewhere around the die in the package, around the package, very close to the processor. Linear regulators may be inside of the die for immediate power management. And then more in the research domain, we still have switch capacitor supplies. Switch capacitor supplies are, here is what they do. Similar kind of a thing as we have done with the inductors. We have a flying capacitor that in phase one is connected in series with the load. We connect in series with the load and we charge it. And then in phase two, we shunt it to the load and we discharge it into the load. We need 4 switches to do this. So we charge and discharge the flying capacitor. As a result, we have a ripple at the output. And this ripple, because this is now the capacitor that is moving the charge between the supply and the load. This ripple has to be of the order of say 100 to 200 millivolts. This can be done fairly efficiently. This whole thing can be done with 90% efficiency. However, it's hard to live with 100 to 200 millivolt ripple. We have done this in research, and we would change the frequency to go higher, then lower, higher, then lower. But that's only in research. In practice, if you're trying to integrate this, the way to remove the ripple, lower the ripple, is to integrate many of these phases. But that kills the efficiency. So from our nice 85–90% efficiency, it drops it down to between 70 and 80. Why? Because inherently, if you put KCL or KVL equations around it, whenever there are multiple phases, there'll be charge sharing happening between different phases, and that charge is lost. If anybody knows how to solve that, you may be able to make some money by providing integrated regulators. Regulators are a hot topic. I mean, there was a Berkeley startup that I think was just recently sold for a decent amount of money that got into, switch capacitor chargers, but standalone chargers, not integrated ones. Lamp semiconductor. Okay, so this exists in research. Now, a big thing that we would like to talk about is interaction between the digital circuitry, the clocks, and the supplies. When the load in the chip, which is our digital circuitry, suddenly changes, that requires the regulator to instantaneously provide more current. For example, when we are ungating a core. So for example, a core has been gated. And let's say looking at cores that we have like here, each one of those may be a few watts. Out of a sub 1 volt supply, that is suddenly going to increase the current out of the regulator by, say, 5 amps or more. Regulators are not able, most of the regulators that are small are not able to instantaneously increase their current from 5 amps to 10 amps on demand. It takes them a while to do that. So as a result, what will happen? Supply voltage will drop. So this is a picture from a long time ago showing what is happening during switching events on the core. So this is an X and Y axis. Now this is not showing a clock insertion delay, it is showing supply voltage as it is by an EMF here. What we see is if it was supposed to be at 1.9 volts, and we see surfaces that are around 1.9 volts. But then we see, some relatively small drop in between where there are compute cores and I can say about 4. Where it drops by like 20 millivolts or so. But then there are some others where there are switching events or part drivers where it drops by hundreds of millivolts. In general, we are looking at the response of a dynamic system to a load change. So what can happen here is, this is a typical model of MSC values for any chip. There is a load here that can have all kinds of changes, PI over DT. What will that do to the entire supply system, regulation system? There is a whole bunch of capacitances and inductances that are out there. So the package and die have their own inductance that are associated with either the bond wires. What is the inductance of bond wires? It's a good number for basically a nanohenry. So if I have a nanohenry worth of a bond wire, and if I try to switch an amp in a nanosecond, what is going to be LDI over dt? It's easy to call with 1 volt. If I have 1 volt supply, it will go down to 0. That's the reason why we don't have bond wire, wire bonded big chips anymore, because split chip inductance is small. It's still a fraction of an atom, so this is again going to be impossible to handle. The way what is helping with those disturbances are decoupling capacitors. So when there's a load change, sudden load change, the charge is not supposed to travel all the way from the input. It's supposed to come out from the decoupling capacitor. Still, slight emergency. So the load is going to, so the charge that is needed here to supply the load is supposed to come instantaneously out of this capacitor. Now these capacitors are not ideal. They may have a serious inductance next to them, depending on the previous situation. Now, we are going to have this decoupling at each level to try to decouple every single one of these loads. So there will be a package inductance that will try to decouple with the motherboard capacitance. And the package capacitors are going to be on the back of the die to try to decouple that. And then the regulator inductance is going to be decoupled with the capacitors that are sitting at the output of the regulator. We have seen these pictures before. There is a whole bunch of capacitors that are typically sitting on the back of a die or around the die. The goal there is for them to come from the charge to come from a decoupling capacitor instead of the regulator. In the supply terminology, and whenever you're going to be, you're likely going to be working on some big chips in your future, you'll find this, you'll hear this terminology. So the first group, second group, and third group that are illustrated over here. The first group comes from the package inductance and decoupling capacitance. Second group comes from the motherboard and package decoupling. And third group comes from the board capacitors. The first group is the deepest and the highest, has the highest frequency. And then the other ones bring out and their respective frequencies. They are at lower frequencies because they correspond to larger inductances that are decoupled with larger capacitances. If you look at on-chip decoupling capacitance, we can't fit that much. We can fit some nanofarads. At most. Well, I can put microfarads over on the board around the die. So in response to a sudden turn on of a core, you're going to see ringing of this entire network. So this is a problem, right? So anybody sees why this might be a problem, and you're going from a 1.2 volt supply that was over here, so drop down instantaneously to sub 1 volt, come back up, and then bring out for some microseconds until it recovers the nominal operating value. What may happen because of this? I mean, the setup time violations all over the place because of the clock not tracking the data. We'll come back to that in a second. And typically, the whole thing is going to run first run slower because it's running at a lower voltage, but it can cause setup time violations and a system crash. So how do you prevent that? Why the cell phones don't crash all the time? Or why my processors, when they turn on, when software turns on cores, it doesn't crash. What happens? So the first thing, they limit DI over DT. There is a good section in MI and M1 explainer, that paper that somebody basically reverse engineered how M1 Apple processor works. By the way, it's a document in Intel processors. Well, M1 takes about 10 microseconds to wake up a core. It is quite a bit of a delay. It's not something that is a lot from a user perspective. It is not really foreseeable when it goes awake anyway. What's the big deal if it takes another 10 microseconds? If it goes asleep for seconds, what's the big deal if it takes an extra 10 microseconds to wake up? So that's how do you do that architecture? Wake it up part by part. We don't know exactly all of that. That has been done. There have been some publications that Intel has done for their Atom processors, but there is an architectural trickery or engineering that is being done to slowly wake up a processor, big load like that. But we are still going to have a drop. So no, this is not going to be exactly a step. It's going to look more like a ramp. And in response to a ramp, this is still going to go down. If you look at the supply voltage will sag and recover eventually. What do we have to do during this sagging of the supply voltage? So these big LDI, if you go and do the analysis in response to a ramp, instead of a step, you'll see that will attenuate the first. So the first drops are going to be much less. But this big one is still going to be there. And it is going to last, again, some microseconds to tens of microseconds. What do we have to do there in order to avoid setup time violations? We have to slow down the processor or slow down the SoC in a controllable, controlled and predicted manner. So every time we are enabling a load, a large load that was asleep, we need to slow down everyone else. Before that, a few other things related to the PLLs. There are a few shocking articles, or first, there are some people have noticed back in the desktop processors, somebody was playing with those. Remember how, back then in desktop processor, nowadays you have an array of capacitors on the back of the die. You buy an Intel or AMD processor, and there's a whole bunch of capacitors on the back of the die. Some people have found out, and including Intel research, that if you pop out a few of these capacitors, die would run faster. The chip would, be subject to more to better overclock. People came up with that, how to pop out a few capacitors to get better overclock. What was the magic? The magic there was to get the PLL. So the PLL was typically tied to a separate supply voltage. And that led to the die supply would sag, and the PLL was not slowing down, and that was a problem. What they wanted, what they managed to do by doing this scientifically is to add more of a high frequency response to the PLL's VCO by mixing in some of these varying supply voltage. So what would happen there would, as the supply voltage would drop, the PLL will track that and recover. Related to the transfer functions. It is not trivial, but it is very worth reading this kind of a paper where you basically want to frequency track certain frequency response of the supply voltage. So that helps, right? So as my supply drops, this is kind of working automatically. The PLL tracks. Now this breaks down in certain cases. I'll skip this. This breaks down in the case where clock insertion delay is longer than the period and it takes multiple clock periods. What happens there? Even if I slow down, now my PLL clock. The clock that is being seen by the loads is the clock that was issued by the PLL like 2 seconds ago. If it is a fast clock and my logic supply has already sagged, in a while now you can analyze exactly what is happening here. We have all the equipment, we have learned everything about that in this class. So we know what is the response of the to what kind of frequencies or what kind of frequency shapes or voltage shapes does our clock distribution network respond, and what does the logic network respond. If you look at the clock distribution network, it is of a certain duration. Its response is the extension of a delay is proportional to its length. It may be, it is typically longer than our logic delay. You can model this. In some cases, it will compensate each other, and this is a great paper that I've linked to it. It takes a little while to understand it through a concept of clock and data compensation. They have done in this paper in both time domain and the frequency domain, showing that depending on the length of the clock insertion delay, in some cases the phase will lead, sometimes it will lag, depending on what kind of a frequency. If you hit some kind of a resonant frequency, they will perfectly cancel each other out, but in some cases they will not. And you will find out when it does that favorably and when it does not do it favorably. It takes quite an effort, and I'm running out of time to analyze how this works. So modern systems essentially incorporate all of the above. Slow down the wake up events. To analyze, which frequencies matter after that when the drop happens. By slowing down the wake up, we have limited the size of the first drop, and then through the clock and data compensations, we have understood what is the logic needed that needs to be added to that. And then we need to adjust to this long drop. This long drop we have sometimes to react to. The way how we do that, we build an analog drop detector. And here is a simple example of a drop detector. It compares the supply voltage with some reference and tells the PLL to slow down for some period of time while the voltage emergency goes through. The supply stabilizes and we pick up the maximum frequency. You will see if you go to ISSCC these days, and this year's and last year's ISSCC, pretty much every processor has a mention of a probe detector indicating. And you've seen a few years ago, they were typically were criticizing like Samsung processors that would drop during the voltage transient, their clock frequency to 1/3. And then you can see the improvements that they would go to 1/2, and then now they pretty well track what is happening to the supply. So this kind of summarizes many topics that we have covered in this class. So we have talked about, in this lecture, we have talked about a lot of things, and many of them should come natural. You have the apparatus. I did not go through the math and derivations of all of this. But we're talking about synchronizations and disputing. So we talked about DLLs, how they're being used in different shapes and forms to dispute signals. Modern SOCs are globally synchronous, locally synchronous, and we have to resynchronize them. We do them through asynchronous clock crossings and async FIFOs, but we also may have rational clock crossings as an intermediate form. We talked about supply regulators and how they can be integrated and how they have to live around the die. And this really hot topic nowadays of supply and clock interaction. That long paper really summarizes many topics of this class and mixes in perhaps a few other classes in order to understand it. But you have all the tools now to understand why does this happen, how this happens, and how do we mitigate impacts of that. And yet another campus-wide alert. So we'll wrap it up here.